Good morning, everyone. Thanks for being here. My name's Danny Scull, and on behalf of my team and Professor Tjossem, I'd like to present our findings on upstream emissions in the electricity sector. This was a project we worked on with the Sierra Club, specifically the Beyond Coal campaign, whose stated goal is to retire the nation's coal plants over the next 10 to 15 years. So I'd like to thank Joe Daniel and the Sierra Club team. They were excellent to work with, really fantastic experience. So this morning I'll start with an explanation of what upstream emissions are, and a little bit of context about why they're important, and then I'll get into our project and the scope and boundaries, as well as some of the problems we ran into throughout the course of the semester. And I'll finish up with some data analysis and our recommendations for both the Sierra Club and the gas and coal industry in general. Now, we all know what combustion emissions are. This is when you burn coal or gas to produce electricity, and it emits CO2 into the environment. This is bad for the climate. Upstream emissions are the greenhouse gases produced in the extraction, processing, and transportation of fossil fuels from their point underground to the power plant, so before they're combusted. You can think of like machines that scoop coal out of the ground and emit CO2, or gas pipelines and wells that leak methane into the atmosphere. These need to be accounted for, and so far there's not a great mechanism to do that. And this is important because the U.S. is responsible for about almost a quarter of global emissions as measured in CO2 equivalent, which takes into account the warming potential of different greenhouse gases such as methane. Within the U.S., the electricity sector is responsible for about a third of emissions. And breaking that down further, you can see coal and gas, basically about 99% of all emissions in the electricity sector. Now, I highlight this because this is a significant chunk of global emissions. The U.S. electricity sector is a pretty big chunk. So it's important for policymakers to have accurate data and an understanding of what this means. And this only reflects combustion emissions. It doesn't take account for the upstream emissions, which is what we studied. And so policymakers really aren't getting an accurate portrayal by only looking at this data. It's only been a few years since people have kind of started to think about this. And I want to highlight this paper from a few years back, a Cornell group who analyzed that natural gas had a higher warming potential than coal. Now, this was based on some limited data. We actually spoke with the author, the author of the paper, about some of the assumptions they made, and he had custom formulas to calculate this. And this actually includes combustion and upstream and downstream emissions of residential heating. So he kind of crossed the streams there. So we don't necessarily agree with this analysis, but it does sound the alarm a little bit that there's something going on with upstream emissions that we're not really taking account of. We don't know enough about it. So that's kind of where we came in. Sierra Club is interested in learning more about this topic, so they asked us to survey all the literature available to find as many greenhouse gas emissions factors as we could, identify and quantify them, and come up with a way for accounting for them. So the way we did this was to create a model where we could input all the data that we found and then standardize the units, so you could kind of do apples to apples comparisons, and then calculate regional averages, national averages, and the best part is that Sierra Club can continue to add data into the model as it becomes available, so their estimations will only become more robust over time. But in collecting this data, we learned a lot about some of the regional factors that contribute to variations in upstream emissions. So, for example, coal, there's different coal mining extraction methods, and I'll walk you through a few. In the Appalachian Basin, you've got underground mining, so there's not a whole lot of land use change, but they're digging very deep into the earth, hitting methane coal seams, and emitting lots of methane, whereas out west, you have more surface mining, so there's more land use change because they're really scraping at the top layer, but less methane release. And mountaintop removal, for example, if you blow up a mountain, it goes from a huge carbon sink to a carbon source, just instantaneously. Another factor to take into account was the differences in heat content of different types of coal. So if you have coal from Wyoming and you need a little bit more of that than coal from Appalachia to produce the same amount of energy, then you need to dig up a little bit more coal in Wyoming, which means there's more emissions per unit of energy as compared to the Appalachian coal. Natural gas, regional factors came into our model as well. So different shale plays had different gas compositions. You might have 97% methane in one region versus 70% methane in another region, and there's different warming potentials that are associated with those compositions. And then Yeah, another factor, down in the Haynesville Shale in Louisiana, it's under immense pressure. So as soon as it's tapped, it starts leaking like crazy, and so they have high production there, but also high leak rates. It's also worth noting that once natural gas is processed, it's basically pure methane at that point. So if and that's what they put in the big interstate pipelines. So if that gas leaks, it has a little higher warming potential than gas that leaks directly from the wellhead or where it's being produced. So we had to take that into account in our model as well. So once we compiled all this data, we realized that there were some obstacles to calculating it, and this stems from, well, methane, for example, it's measured in different ways. You've got satellite data, you've got aircraft data with infrared cameras, you've got people measuring valves on the ground, and all of these are reported in different units with large margins of errors. And some of the assumptions in the findings we found were kind of all over the place, so we had to really watch out for that in compiling our data. But I want to draw your attention to methane in particular. This is kind of the major offender here in upstream emissions for both coal and natural gas. And it's a very powerful greenhouse gas, 86 times the warming potential over a 20-year period compared to carbon dioxide. And it's reported different ways. So you've got hourly flow rates where you can identify at a given point in time what the leak rate is, but it doesn't really say much about the total production of the leak. And you've also got percentage leak rates where you can say, okay, this region leaks 2% of their gas or 3% of their gas, but you don't get the time scale. So we had to do a lot of kind of converting back and forth to fill out our model, which was pretty tricky. An example is in the Denver Shale. They have a high hourly flow rate, but low production rate. So it's really hard to judge what the actual climate impact of the leak there is. Another variable to take into account was venting versus flaring. When in the fracking process, you have to release some of the gas for safety reasons. You don't want the well to blow up when they're fracking. So some wells will vent this directly to the atmosphere. Some will burn it off as CO2, and some will capture it. And the papers that we read had wildly different assumptions about how much is captured versus how much is flared versus how much is vented. So that was something we had to make our own assumptions about in developing our model. Super emitters were another major problem for us. An example in the Barnett Shale in Texas, I think it's 0.06% of the wells there produce 50% of the methane emissions. So this really skews regional averages. You might have thousands of wells operating responsibly with low leak rates, but then a handful that are leaking like crazy and totally throw off the averages. So it's worth noting that this is why regulatory measures have been in place for the last few years, but President Trump actually just rolled back a lot of the methane emissions that the EPA had in place. So our data analysis, after we kind of fed all of our information into the model, came out like this. So this is just combustion emissions. This is your classic natural gas, has about half the carbon footprint of coal, just purely based on combustion. But once we ran our numbers and then added in the upstream portion, it looks more like this. And you can see that natural gas has about 3/4 of the upstream footprint that coal does, or of the life cycle footprint that coal does. Now, this you can see, coal is still a dirtier fuel here, especially when you take into account the local environmental pollution that it produces. But I guess the takeaway would be that natural gas isn't necessarily a great alternative. It's still most of the warming potential of coal, so that's kind of something to keep in mind as far as climate policy goes. It's also worth noting that a lot of the more recent papers we looked at had higher values for natural gas, so I think as the data gets better, you might even see that natural gas number skew out further to the right. So in compiling the data, we have a few recommendations. First of all, there just aren't enough regional studies to really do a robust analysis for regional averages, so we recommended Sierra Club just use as a national average for the time being. Lots of the studies are reported in different units, so we want the industry to standardize data reporting to make it less confusing. That was like a huge problem for us. Lots of the studies only look at certain steps in the upstream emissions process, so we recommended the Sierra Club fills in those data gaps with averages from other studies. And then finally, the super emitters, really the only way to account for those is to average out across many studies to kind of increase the sample size so that they don't have such an impact on the data. So that's about it, but I want to kind of close, well, I have a closing thought. a lot of climate policy in the U.S. is really based on the assumption that gas burns cleaner than coal, and it does. That's true. But it doesn't really give the full impact of what it means to produce electricity using these different fuel types. So next time you're talking about climate policy or emissions policy in particular, it's worth keeping in mind that there are things that are not being accounted for that you have to look out for in the data. So in any case, that was our project, and I hope you enjoyed the presentation.
I was just wondering if you think these upstream emissions can be mitigated by policy, or if we just don't have the technologies right now to reduce them, if you've seen that in your research.
So, what's that? Oh, so she was just wondering if there are technology or regulatory measures that can be used to mitigate upstream emissions. Is that correct?
Yeah, if you think we have the technology to reduce these upstream emissions and just don't have the policies to enforce it, or if we just don't have...
Right. So I mentioned we spoke with the one professor at Cornell who had some things to say about this. So the technology, at least for the venting and the flaring, which is a huge part of the methane emissions, the technology is there. And according to the different, if you ask an industry source, they say we capture 93% of the methane vented at the well. But if you actually look at how much of that equipment is sold around the country, it doesn't account for, there's no way it's capturing all that gas. So the regulatory measures are, well, at least prior to last month, had been starting to catch up with this. And I think there's an argument that industry is incentivized to capture. I mean, that's what they're selling, right? So they would want to capture the gas. But part of it has to do with, I didn't mention it, but the marginal cost of basically capturing the gas versus just building another well. So if it's cheaper to just build another well, then that's what industry is going to do. So there does need to be regulatory, regulations in place. But we'll see what happens with the EPA. I don't know.
Can I go?
Hey, Louise.
Hi, Danny. Thanks, that was a really interesting presentation. So it sounds like from what you're saying that all of the kind of inventories and things that we have in the US are just quite materially understated if we're missing the upstream emissions. And what does that mean, or did you and your group have a chance to think about what that means for climate policy goals, commitments, that kind of thing?
So I guess as far as the broader policy goals, we talked with the Sierra Club a little bit about that. They said, hands off, that's our job, you don't need to think about that. But as far as the existing inventories, so one thing they actually wanted us to do was look through the EPA inventories and see, okay, how do their numbers stack up with what we're finding? And the EPA has done a good job of updating to try and take more account of the upstream emissions, but there's been a lot of studies funded by EDF over the last, I think, 4 or 5 years. And they're small sample sizes, and honestly, we couldn't use a lot of them in our model because of the way that the units were reported. But what they were showing is that, at least in small scales, on given days, that the upstream emissions were way higher than what the EPA is saying. So it really just requires, it's going to require more research, but there's reason to think that maybe this is understated for the time being. Mr. Bostic?
So I'm sort of thinking of Volkswagen and defeating emissions controls for Volkswagen. Do you think you could have a similar case in power production, where you go and the regulators measure something and then they kick it up a notch to actually run?
I suppose that could very well be the case, but really the problem now is that there's just not nearly enough measuring going on in the first place. It's very costly to measure this kind of stuff. You need really expensive equipment, and there's just so many wells and so many pipelines, and you'd have to measure every single valve and compressor, and it's totally unfeasible. So a lot of it is self-reporting from the industry, which is not exactly reliable. Like I said, their numbers are very different from kind of the independent research that's been going on. But so I don't know. We'll see.
Wonderful presentation. Before we take a break, I want to put my 2 cents in, which is that you don't inspect every party when you regulate. The IRS doesn't do it. Nobody does it. You do enough to scare people that they might get inspected. And the problem with the kind of enforcement we're seeing now is that there's no threat. All you have to do, I mean, the United States has a very high rate of tax compliance, and they inspect far fewer than 1% of the people that file their tax returns. So it doesn't take much, but you got to do something. And so we don't have to have every valve looked at. We just have to make people think, oh, my valve is going to be looked at today.